before climate change, this event would have happened but 1 in 250 years. But now, as we get towards a 2-degree warming world, this will happen sort of every 1 to 5 years, these kind of events.
It's my pleasure to introduce Scott Hosking. So Scott is the Mission Director for Environmental Forecasting at the Alan Turing Institute. He's also founder of the British Antarctic Survey AI Lab, and he led the first team to develop, the team that developed the first AI-powered pan-Arctic sea ice forecasting model, a model called IceNet. He's also been pioneering a model called FastNet, which I'm sure we'll hear more about, which is AI-based weather forecasting, where he's been working very closely with the UK Met Office and doing many other exciting activities around AI-based weather and climate modelling. So over to you, Scott.
Thank you, Jason, and thank you, everyone, for coming today. It's great to see so many people here at the Royal Society. So my talk, I use the word messy data, and that shouldn't be disparaging of all the people that collect the data. It's just very messy. We work with data from ship logs, data from weather stations, including in the polar regions where they're pushed over by polar bears and things. So there's a lot of messy data out there, and a big part of our work is how we make sure that data is usable for AI-ready data. So let's jump in. So 2025 was a heartbreaking year for many reasons. Big extreme events, climate catastrophes around the world. Just to name a few, we saw these fires in California, caused $60 billion worth of damage, more than 400 deaths. Again, we saw cyclones and floods in Thailand, Indonesia, Sri Lanka, Vietnam, Malaysia. 25 billion in losses, more than 1,750 deaths. And then another example here, again, in these tens of billions scales, the floods in China, we saw at the back end of last year. So, and if you start plotting this, these are the $1 billion disaster events year on year just in the US. We are seeing an upward trend. And also I would say that trend is not linear. We as people, as humans, we often think of change as being quite linear. But some of the results and some of the numbers I'm going to show you today shows it's anything but linear. We need to really think about, getting towards more exponential thinking. Zooming in on the UK, we saw in 2022 a heat wave. Temperatures reached 40 degrees centigrade in London. Now, there are many meteorologists, expert meteorologists, climate scientists who did not believe we would reach that number in the 2020s, let alone 2030s. But here we are. We've hit that. We've reached that threshold. I mentioned the idea of linear thinking. So if you look at the cost for flooding alone in the 2010s, flooding cost the UK government around 8 billion, estimated to increase to around 40 billion in the 2020s, and then upwards of 200 billion in the decade after that. So these numbers are astronomical. They're huge. I mean, these are estimates, and this report was a few years old now, but it gives you the idea of the increase in severity, in cost to human lives, cost to our financial security. Now, the World Economic Forum released this report. This is an annual report, so this is the 2026 report, the Global Risk Report, highlighting the main risks in terms of severity. And you can see, there's a number of things on here, including at the top, geoeconomic confrontation, misinformation, we've got societal polarization, extreme weather events are up there. If you look out to a 10-year horizon, the weather events, the environmental events float right to the top. It's quite often we see environment as something we know is important, but it's never the next thing, the most urgent thing. And I think this report, and the fact it comes out annually, and again it happened last year and this year, environmental weather, extreme weather events, biodiversity collapse, and critical change to Earth systems have come out top. So climate change and ecosystem collapse, these are not just environmental issues and challenges, these are also national security threats. This is highlighted clearly in the Ministry of Defence's review in 2021. Now firmly a defense problem, climate change is a significant challenge. Without adequate assessments of its effects, we leave ourselves exposed. I mean, there's nothing clearer than that. In January, just this year, the Biodiversity Loss Ecosystem Collapse report that was released by DEFRA. Critical ecosystems that support major global food production areas and impact global climate, water and weather cycles are the most important for the UK's national security. So this is not a report just talking about weather and climate at home where we grow food, but around the world and part of our supply chains. And then, we know what's happening in the Arctic right now and the challenges, geopolitical challenges we're seeing there. The UK has just announced in February to step up and increase defence activities in the Arctic and the high north. And, make no mistake, this is due to the lack and the loss of sea ice, climate change problem that's underlying this, and we can see that in the decline over the last few decades in that plot there I'm showing. So what are we doing in this space? Our work in environmental security and resilience. We're working with 8 Met agencies, so weather forecasting agencies in Ghana and Senegal, to work with their and universities and supporting the farmers to produce weather forecasts to make their way of life more resilient, so support those farmers in that agricultural community. We're working to make our data more AI ready, and Evie's here, and you can talk to Evie at the poster session if you'd like to talk about the work we've done in UK crop yield data, using satellite data, information from various databases and making sure that data is far more AI ready for our models. Working with the fisheries department within government to help monitor and understand the ocean health around the UK and our fish stocks. I've already mentioned the work we're doing in the Arctic. So last May, I think the Foreign Secretary announced some new research activities, which has led to this AI for the Arctic Security Program in our defense team. And similarly in the Arctic, Jason mentioned this as well, I've been leading the IceNet program, so producing AI sea ice forecasts out to days, weeks and months ahead to support, in this case, working with shipping companies, indigenous communities and wildlife conservation groups. And then just lastly, a couple of others, but work we're doing with DESNES in decarbonisation, and I'm going to mention more about our work with the UK Met Office. Okay, so I wanted to frame this talk around the pillars of the DCIT AI for Science strategy, which was released at the end of last year. 3 pillars are data, compute, and people and culture. And I just wanted to show a few examples and work we're doing that align to those. So one of them in data is curating diverse, high-quality data, making that data AI-ready. I've already mentioned the work we're doing in agriculture. We're working from weather to climate scales, working with, I showed the analysis we're doing with the fisheries community. So diverse data sets, but making sure they are ready for the foundation models we've heard about today. Optimizing complex workflows through sovereign supercomputing. We've already heard about the work that we're doing on the Isambard AI and Dawn supercomputers in the UK right now. Those are our gateway to make those technological and scientific advances, so making sure that those platforms are easy to use and usable by the wider community. And in building interdisciplinary teams, and I've got a nice example of the work we are doing with the Met Office. And there's, spoiler alert, we've got a long author list, and I want to explain the fact that we've got so many interdisciplinary different skill sets is so important to make those advancements. So I'm going to talk about the FastNet model, and this is the model we are developing with the UK Met Office, so what will hope to be the first AI operational weather forecast for the UK. So there's been a rise in the machine learning models over the last 5 years. From left to right, on the x-axis here, these are the dates at which the paper and the model was published. So going from 2019 to present day. And on the y-axis, going up the page, this is the performance metric skill score, if you like. So as you can see, that in around 4 or 5 years ago, the models were closer to the bottom left. And as we've gone on, we're now seeing that they're above this 100%, this 100 RMSE figure. And I should say that, sorry, the y-axis has been normalized to RMSE, and with 100 being the level at which that's the same skill as the European Centre for Medium Range Weather Forecasts IFS model. So anything above that is better than the state-of-the-art best physics model that's out there. So on here you can see a few big hitters. We've got the DeepMind's GraphCast model, we've got Pangu Weather, ForecastNet from NVIDIA is on there. There's the new FGN model from Google DeepMind, and so these are some of the latest models. Ryan Keisler really brought the AI for weather forecasting to the attention in 2022, and that model was so close to reaching this target. So we've built a real community, and there's a lot of international collaboration around these models now. And the FastNet model I'm going to mention, we're up there in the pack. So we're in this above this 100 level I mentioned on the y-axis. But we're also going to talk about why root mean square error is not the only metric we care about when we think about operationalizing. So one of the reasons the weather forecasting community and AI has really taken off is because the data was AI ready. There was this amazing data set called ERA5, a reanalysis product. So FastNet was trained on this. This is a 40-year record of estimating what the weather has done over that time, 6-hourly time intervals, 13 levels through the atmosphere, so different pressure levels through the atmosphere, surface variables. It's an amazing feat of engineering to get all this data together, assimilated in one product. And it's perfect food for an AI model to eat up and to throw onto GPUs. A couple of things to note here. This data set comes in 2 resolutions, depending on how much compute you want to burn through. And we use this reduced Gaussian grid. So that means as you get closer to the poles, you reduce your number of grid points because the grid cells get closer together. So to make the data set more efficient, we use this thinning of data towards the poles, towards those singularities. So data, we've got 40 years. The last 2 years kept aside for validation and evaluation. And this is something the community has all sort of got behind. So when we're comparing models, we're all comparing apples with apples. So let me say a little bit about the architecture we used in version 1. And this is from about a year ago now, but we used a graph neural network. We mapped the nodes on our surface, on each position, to mesh nodes. In the encoder space, and we take this sort of common encode, process, decode architecture. So we take our data from era 5, map it into process space, and this is a reduced dimensional space, which is far more easy to work with. And we've heard other examples today in talks where, in this latent space, in process space, makes much more sense to scale and run large simulations. And then at the end, we decode the residual change in weather, and we add that back to our initial state to progress the model on for 6 hours. Now, the mesh here, you could think of this like a 12-sided, 20-sided dice, but we want climate is complex at different scales. So what we do is we take a lot of different meshes. So we take a multi-mesh approach, and this is based on the multi-mesh approach we saw in the DeepMind GraphCast paper and model. So this is an icosphere. The top left is the coarsest resolution of this mesh that we use. And it's just to illustrate that we take each edge and cut it in 2 and add more and more triangles. So we are getting finer and finer resolution. We couldn't fit all of them and visualize them all. So actually there are 2 or 3 more grids to the, off to the top right up there. And the plot then at the bottom, the figure at the bottom, this just demonstrates when you sort of add them on top of each other. And what's key and important here is that for each point on the coarse resolution mesh, it maps directly on top to to a node on all the other mesh. So that really helps with the message passing across the multi-mesh. And because of the different resolutions and granularity in your mesh, you can encode both long-term connections and short-term connections. So here's a little animation of our model. We've got the ground truth on the left-hand side, the era 5 truth. What's the estimate of weather for the last 40 years? And then our model on the right. And the first thing you'll notice is our model is smoother than the model on the left. Now, one of the problems using a mean square error function in our loss function is this smoothing. We get this double penalty. So if we predict a storm in the wrong place, we get penalized once for making a wrong prediction and then again for missing the right prediction. So if you're a model that's based on RMSE, the best thing you do is hedge your bets and spread things out, and you get this sort of smoothing. And this is not unique to weather forecasting. So then the next thing we did is, because we're working in partnership with the Met Office, is to also benchmark this against their current global forecasting model, so the global Met Office global model. And this is what we're showing here in this graph. So on the x-axis on the bottom, this is the relative skill again. So anything to the right, the FastNet model performs better. Anything to the left, the traditional physics-based model does better. And on the y-axis, we have different weather variables, so temperature, winds, pressure, etc. And then the numbers in here are the lead time, so forecasting up to 7 days ahead. So these are in hours here. And one thing you'll notice is, well, we do a pretty good job across the board, apart from geopotential height. But we also peak around 48 hours, and this is the longest time at which our model was fine-tuned on. And there's, in the paper, you'll see why we chose 48 hours. But that's how we're doing, out to 7 days at the moment compared to that model. So you can see now, the challenge is now working towards operationalizing this and getting this out there with the Met Office. So there's a poster here today for those who are in person in the audience, and you can talk to the team. But we've also made some improvements to the modifications to the loss function to improve physical consistency. The 3 areas are the spectral biases and blurring that I've already mentioned, the double penalty, and we can talk more about that later. The slow wind bias, so this is something that's known in many models, that if you're trying to optimize for both wind direction and wind speed, again, if you want to, by getting your model, by just slowing down your winds, you're more likely, you're going to reduce your error, and that's just the way that RMSE works. It's not exactly what we would want, but it's what we've told the model to do, and it's not wrong in that, but it's just not exactly what we're looking for. And then there are these forecast artifacts, and I'll say a little bit more about them now, but this is where the sort of underlying construction of the mesh starts to appear and surface through the features, which of course is undesirable, but it's something nonetheless that we see. So these are the model artifacts. So let's start with the GraphCast model from DeepMind on the left, and I should say these are known, and I'm not, all of these centers have highlighted this is a known problem, so this is not pointing any fingers at anyone. But GraphCast recognized this, and we see this hexagonal honeycomb-like structure, and this is, again, because of that mesh appearing through our outputs, and it's particularly evident in fields with a horizontal gradient, such as the winds. Pangu weather, similarly, we see these artifacts, and here we see a shifting window transform, a vision transform, and you can see that window appearing in this output here, and ForecastNet similarly uses the same kind of underlying structure. And then there's this FGN model from DeepMind, and what I liked about this paper as well is pretty much the last figure, they held their hands up and say, look, we still got this honeycomb-like pattern. And it's harder to see, but nonetheless, it's something that's in the output, and it's not desirable, it's not physically realistic. So I can show you that now and how it appears in our baseline FastNet model before we delved into the loss function and modifications. So here I'm showing an animation of wind speed in the contours and then the pressure contours. And you can see these pressure contours are jagged. That's not realistic, but this is what the model has produced. So these are wind speeds, and then here's the geostrophic wind speed. And it's far more evident now in this field that we get this honeycomb structure. And so one of the things we look to do, and the Met Office, rightly so, we're keen to tackle this to ensure that we can reduce this if we're going to move the model towards operationalization. So yeah, if you now overlap and overlay the grid cells from the internal mesh, you can see it lines up exactly. So we know why it's happening, and we can see this in the spectrum as well. So let's dive in and tackle that. So I won't go into too much of the details here, but on the left-hand side, you can see that frequency, those wave numbers, and we see that in the blue here. I'll use my mouse to sort of highlight this. The blue here is the model before we introduce this new sort of modification of the loss function. You see a bump in that, the further away from zero, the larger the error, and the green lines there where we reduce that error with our new horizontal loss function gradient loss term. And if you again comparing the images here, so era 5, this is our ground truth data set that I mentioned earlier. You compare that to the fields to the right of it, you can see this, again, these artifacts, these textures showing through in the output. And then on the bottom here, after we've introduced our new loss function, we smooth these out. So this was one of the key parts of our paper to make the models more physically realistic and therefore usable in terms of operationalization. And I mentioned earlier that there were these 3 terms: the spectral nudging, the slow wind bias, and then these artifacts. And when you add many different things to a loss function, it's not clear that if you add them all in, it's actually going to help, and they might contradict or fight with one another. Well, actually, they did work fairly well with each other, and this is just demonstrating that on the bottom here, if you bring them all together, it does improve the physical consistency without taking a hit on the root mean square error, which is this skill metric that all of the models are using. So that was a win-win. We were able to meet the metric, but at the same time making the model more physically consistent at that local level. So that was our FastNet model, and we have a poster here today, and there's going to be a lightning talk after as well, so we can dive into that more. Now I want to move on to national resilience for data sparse regions, and this links to the messy data that I mentioned earlier. So we're developing weather forecasting models for the UK, but we're fairly lucky in the UK. We have a lot of data, a lot of weather stations. We have amazing radar to detect rain, and we've collected observations for decades. So, in the global north and, other parts of the world, we have these amazing data sets. But what about Sub-Saharan Africa as just one example? How do we build models that are uniquely optimized and developed for those regions? And that's what we've been doing with this aardvark weather model and working closely with Rich Turner's group in Cambridge. So this model took a different approach. It didn't start with that era 5 nicely gridded uniform data set. It learned directly from those raw, messy observations, including satellite data, weather stations, data from ships, and SONs. So, this is a highly imbalanced data set with lots of gaps and fragmented data. And we see this, again, this standard encode, process, decode structure. So we encode this data into a grid, process this forward through time, through different time steps, 6 hours, 12 hours, etc. And then this model decodes that back down to a weather station. So actually, you could almost think of this as having infinite resolution, where if you want higher resolution in one place, we can use all our compute power and optimize for that location. And the model's built with to learn context from different parts of the world. So if there's a region with lots of data and it has a similar context to the environment you're interested in, then that transfer learning comes for free. Now, this was one of the most surprising bits of this work, where I mentioned earlier the Sub-Saharan Africa is fairly data sparse. So if we were going to learn directly from data, you'd think it would do a poor job. But actually, the model here had a lower error compared to the physics-based model that we compared it with at the time, the ECMWF's high-res model. So the purple line here is this aardvark weather model. The orange is comparing that to the physics-based model. We've got lead time forecasting forward up to 10 days on the x-axis, and then on the y-axis here we have this our error metric for temperature on the left and then winds on the right. So this was actually surprised us, like how is it doing so well here? And the sort of current thinking is that because our models are sort of so biased, learning from where we have a lot of data is actually smearing out a lot of the physics, because the physics in Sub-Saharan Africa are very different to the US, to continental Europe, where we have a lot of our data. So actually, there's a lot of, this is demonstrating there's a lot of physics missing in our models, and learning from data and physics together has to be the way to go. This paper was picked up by over 50 outlets, and we even got a shout out for the Minister of AI, Farrell Clark, at the time. And we sort of see this as a second wave of weather forecasting, learning directly from data. And I think now the third wave is how we bring physics into that as well. So I mentioned the surprise result in West Africa, and straight away we started talking to the Gates Foundation, who we knew we had set up shop head offices around Africa, to think about how we work with their agricultural sort of networks and communities. So this really sort of helped broker that relationship. So we are working now very closely with Doug Parker and Rich Turner from Cambridge. We're working with the Met agencies and universities locally, European Centre for Medium Range Weather Forecasting, Met Office, etc. So it's a real huge team effort, a large program of activity. And this here is an 18-month pilot. So can we take our model, and we're not here to develop and improve the machine learning as such. I mean, that we will, that we have to, but it's more about how we listen and understand the challenges and what we have to do to the model to make sure it's usable by the meteorological weather forecasting agencies. So there's been a huge effort to not just take our model and say, there you go, how we can start thinking and redesigning it from the ground up. Now we've demonstrated the technology could work. So now back to the FastNet model with the Met Office. I mentioned the importance of learning directly from data. So this is our next phase for the Met Office. And again, you have to put a lens on this. We don't want to just develop a model that gives us the best root mean square error sort of metric at the end. We also need to think about how we can operationalize this in real time. And operationalization is also one of those words that means different things to different people. But if you say to the Met Office what operationalization means, you've got to think of someone or a model that if there was an issue with it and you picked up the phone at 2 a.m, there's someone there to answer the phone and help and fix that. It's not something that's running on a website and could fall over, but we'll pick it up in a few days' time. It has to work. And it has to work with almost zero challenges, and always have someone there to pick it up if it falls over. So what we're doing with FastNet here is we are at time 0. We are feeding in this global data, the ERA 5 data, or the global Met Office model data. But we're now also, the next plan is to feed in the observational data like I just showed with the aardvark weather model. So, once someone's demonstrated in one model that you can do this, it makes sense to put some energy and effort into it. We've seen the benefit. But what we're also doing is learning from the UK Met Office's high-resolution UK data. So this 1.5 kilometre resolution. And it's an amazing data set. There's so much information and sort of encoded physics in that data set of how storms move, the storm fronts, etc. We want to incorporate that into our pipeline. So the challenge is, though, to get that data requires a lot of data assimilation, a lot of time, and we're unable to assimilate that in or incorporate that into our model, operational model at time 0. So we incorporate that in at time +1, and we have this dual encoder approach. That's our plan, at least. Now, we're working closely with colleagues using an open source framework across Europe, Anemoy framework. And this is a big step up or big change from version 1 of the model, where we're now building on this common infrastructure. And what this means is if another member of the ECMWF or EU develops a model in that framework, we can get that for free. We can use that and we can collaborate far more easily. And the acceleration in our work has just really stepped up a notch because of that open source and that working. Right, and I'm just going to say a few things on moving towards climate prediction. So the weather, I just mentioned the 40 years of data, but you've got to remember this is a blink of an eye in terms of what the climate has been doing over the scale of centuries, over millennia. And we really need to know what's going to happen months, years ahead, not just the next 10 days. So, this example here is we are forecasting into the unknown, and we really need to bring that physics in. And I just wanted to highlight why, this is so important. Climate change is a threat multiplier, and this is a sort of clear example of the work of what we saw in Syria in the late 2010s. So the droughts persisted for between 2006 and 2010. We saw 60% of the nation turn to desert in that time. Cattle died, 80% of the cattle died by 2009. Hundreds of thousands of farmers moved into the cities, and we've seen the tensions and the civil war and the challenges that have broken out as a result. So a lot of conflict and migration around the world is sourced in climate change. So we really need to be able to provide that information ahead of time. It's no use going back and saying, oh well, there was a change in this climate mode and it interacted with a low CIC over here. We need to be able to forecast that and have that foresight. And just to highlight just how abnormal that is, so before climate change, this event would have happened but 1 in 250 years, but now as we get towards a 2-degree warming world, this will happen sort of every 1 to 5 years, these kind of events. And again, this goes back to what I said earlier. We often think linearly when we think about climate change. It's far from linear. So I'm going to talk about some of the other work, and I'm highlighting this model, something we've been working on, so I know about, but we're also so the Aurora from Microsoft team, there's a climate in a bottle model from NVIDIA, the ACE2 model from Allen Institute. These are all models that we've been working with, but this model particularly is one that we've been contributing to, so I can say a little more about it. So this is a foundation model. We heard about foundation models earlier, but a foundation model for weather and climate, and it's incorporating weather and climate data sets. So to say something about the AI ecosystem, so it was fantastic when these models are open source, because it means we can, they're fair game. We can start using them, play with them, fine tune them, adapt them, etc. So this model was open sourced by Microsoft in mid-2025. And since then, we've been using the model for a lot of our own research, so the work we're doing in West Africa, for instance. But as a national institute as well, with a large research software engineering team, anything we develop, we want to make sure it's out there for the wider community. And as it turns out, sort of quite by accident, but 70% of the code contributed to the main branch has come from our team in that time, because we're using it for our science, for impact, but we're also making sure that everyone gets the benefit from that work as well. So yeah, we're developing, porting, testing models, and very much to deliver impact, but because we are a diverse team of researchers, software engineers, data wranglers, project managers, we're making sure that benefit is seen far more widely. And we're working very closely and have projects now scaling up on Isambard and Dawn. And we were one of the first teams actually to be running on Dawn with our IceNet model. So now going back to the AI for science strategy. So I've already talked about curating diverse, high-quality data, and this is far more. This becomes hugely important in data sparse regions where those data sets are not always available in the format you would like. Optimizing workflows, and the last thing then is people and culture. And I wanted to say a little bit about our work with the Met Office, and I think this has been a really good example or a template of how we can do this work and how we can make AI and work for large teams. So our paper will be out soon. Our preprints online, and we've written a report. But I wanted to highlight, there's a large author list here. And this is because we do need that diversity, that we've got interdisciplinary teams. And in there, we've got physicists, meteorologists, operational meteorologists, data wranglers, machine learners, cloud engineers, etc. This is a huge effort, and different people will need it at different parts of the process. So this is why setting something up like this isn't to be taken lightly. It took a huge effort. And then a big shout out to our project managers who made this happen. I mean, they're almost on the phone to each other every day, every other day. There's to keep a big project like this ticking over. It's so important that you build up those relationships and you have people who can fix those problems when, and push things forward. The team, they again also have bi-weekly stand-ups. We're heading down to Exeter. They're heading up to the British Library each month, every other month, to have the in-working sessions. We work in sprints as well, and it really focuses the mind, like what is this team at any one time of 10 people going to focus on for this next sprint and get that across the line. And it really brings everyone sort of together and really focuses our minds. So I focus on interdisciplinary teams, stand-ups, and these are things which I think are a real template for scaling an AI project. We've also had master students working with us, and they've moved on and secured new jobs themselves, which has just been amazing to see. Team members have joined startups in that time. We've got postdocs now leading their own projects, EU projects, and we had a new assistant professor as well. So, I mean, actually, I'm going to stop on that slide because I think that's been something we're personally and as a team very proud of. And just lastly to say thank you to UKRI, EPSRC for funding this or supporting this project. And I'll stop there. Thank you.